students, we're going to dive right into Unit 4, and today we're going to be talking about the introduction to sensors and motors, and we're going to be using a simulation for a Copier Jam detector to do that. So let's get started. So if we were in our classroom, we would be using our VEX kit to simulate a copier. So over here, you can see how it would be set up. We would have 3 limit switches set up in succession, followed by a gear and a motor. Now the gear and the motor are there to represent the actual motor of the copy machine. And the paper path would be from the right to the left, and then all of these switches will be wired as normally open. So when paper makes contact with a switch, it outputs a logic 1, and when it's not touching it, when the paper is not touching a switch, it is a 0. If a jam occurs, it stops the motor, and that's why we have the gear and shaft attached there in a real world situation. So that way you could see whether or not the motor was turning more efficiently. Now, under normal operations, you would need 2 adjacent switches triggered in order to indicate a jam. So anytime that you have a single switch triggered or a space between the 2, it does not indicate a jam. So you can see all the instances of the jam over here on the right. You'll notice that it's only when we have 2 adjacent limit switches triggered do we actually indicate a jam. If the sensor in the middle is not triggered, then it does not indicate a jam. Now the motor output should remain on until the copier jams, and the copier only jams when there are 2 adjacent inputs triggered. So when a paper jam occurs, an LED indicator light will turn on, and optionally a buzzer will sound. The LED should remain on and the motor off until there's a clear button pushed. This will require a push button to be latched with a flip-flop. Now we haven't done a whole lot of flip-flop work, but you'll get a chance to today. The design should include pull-down resistors, and the design should include a voltage divider that changes the signal voltage from 5 volts to 3.3 volts. That's because some of the components from the VEX do not run on 5 volts, so we have to separate those two. And the design should include a quadruple half-H driver and a full bridge driver, and then 6 volts external voltage to drive the motor. So we'll take a look at all that in a little bit. Now, if we were in the classroom, we would be using our S7s to program this, as well as our MIDACs, and we would be attaching those to the VEX components. So we would be inputting the wires that way, but we would actually have 2 separate power sources. One would be for the S7, which would be through the USB port, and then we would be using power supplies to provide external voltage for the VEX parts, which is what this slide is explaining. Now, one way to reduce the 5 volt provided to the 3.3 desired is through a voltage divider. A voltage divider is a linear circuit that takes voltage and takes an output voltage and turns it into, which is a fraction of the input voltage. So if you look at the schematic below, this is an example of a voltage divider. Now the other thing that you're going to need in this circuit is a pull-down resistor. So this is another way to help distinguish between high and low signals at the inputs. So pull-down resistors hold the logic signal near 0 when no other active device is connected. And you can see we have put in pull-down resistors right here inside of that part of the circuit. Now, if we were using regular switches, okay, the red wire in the switch would not be connected on the interior. The switch is wired as a single pull double throw, so it only uses the black and white. And that's how most limit switches are set up. Looking at the motors, you guys have seen these VEX motors before. They require more than the 5 volts using the TTL logic. So that's why we would need the external power supply to power that motor. Now, what's an Hbridge driver? Okay, aside from keeping the motor voltage source separate, we still want to make sure that the motors are able to move in both directions. So an Hbridge is an electrical circuit that enables a voltage to be applied across a load in either direction. So these are 2 examples of an H driver, and you'll be working with those in your circuit today. So this would be the wiring for the SN7 So that would be the IC chip that we would be working with in conjunction with our S7 if we were in the classroom. And then here's your block diagram. You're going to be taking a closer look at this block diagram inside of Tinkercad today to replicate this circuit. For the most part, this is going to be the same. You're going to have to use some other logic to create the PLD portion because we don't have options for PLD. Now, taking a look at the equipment that we would use if we were in the classroom working with our VEX kit, we would ultimately end up with this. So you would have your MyDAC wired. This is your S7. You can see it's wired externally. And then we would have the VEX parts wired into the different components of the S7 that are powered through that 6-volt power source. So the S7 would have power coming in, and this chip would control all of the components here. So once the circuit was powered, the logic control would all be based inside of here, as well as this one IC chip here. And that's what would allow us to trigger the limit switches to indicate whether or not we had a jam. And this just takes a closer look at the physical wiring. You can see these are our pull-down resistors right here. And we are working within that IC chip right there to make the logic flow through into our circuit outputs down here into the motor and the limit switches. And this is just a tighter, more up-close view. Now, this is what you would be working with if we were still in the classroom. You can see the VEX pieces actually fit really nicely into the prototyping boards. And then we would have our resistor set up across the S7. Now, you can see the LEDs indicated on the S7. That's what we would be using for that LED indicator that I mentioned in the design. S7 actually has multiple LEDs built into it. We could wire them externally, but the S7 also has button 1 and 2, and we would be using one of those as our clear inside of the classroom if we were setting this up. So that is it for the physical wiring overview of what if we were still in the classroom. Now I want you to continue in the activity guide and follow along with a video provided from one of Project Lead the Way's master teachers to set this up in Tinkercad. See you soon.